Let's learn a little bit about the coolant. Coolant is very vital to machining on a CNC. The coolant provides lubrication for the cutting action, cools the tool and the part, flushes chips away from the tool. This is especially true when drilling holes. And it sometimes offers rust prevention. The rust prevention is a chemical that's built into the coolant that keeps the machine tool from rusting as well as the workpiece. Programming the coolant to come on and off is very simple. We use what is called an M code. For turning the coolant on, we would command M08. To turn the coolant off, we would command M09. Some machines offer more than one coolant pump. In situations like this, you may have several different M functions to turn different coolant pumps on and off. The reason they allow for different coolant pumps is to allow coolant to flow at different locations within the machine tool. On almost all machine tools, the coolant is plumbed directly to the cutting tool through the turret. On some turning centers, they also provide an auxiliary coolant hose that blasts coolant directly onto the workpiece. Now let's take a look at all the fascinating things we can do with the spindle. As you view the spindle from the front, as we are here in this photo, counterclockwise would be forward rotation. Clockwise would be reverse rotation. To turn the spindle on is quite simple. M03 turns the spindle on in forward rotation. M04 turns the spindle on in reverse rotation. M05 stops the spindle in either case. Controlling the speed of the spindle is a little bit more complicated than just simply turning the spindle on or off. On a CNC turning center, we have two different ways of controlling the spindle's speed: constant surface speed and direct RPM programming. Constant surface speed takes into account that as the tool is cutting different diameters, the RPM of the spindle needs to change. This has to do with the change in the diameter of the workpiece. As you can watch during this animation, the tool starts out cutting at a 1/2 inch diameter, but by the time it's toward the end of the workpiece and at the end of the finished path, it is cutting a 1.2 inch diameter. Now, at the 1.2 inch diameter, our circumference of the workpiece is much greater than it is at the 1/2 inch diameter. Constant surface speed deals with the circumference of the workpiece. The circumference of the workpiece is considered the surface area of the part. Calculating the circumference is really quite simple. There's a formula: circumference equals diameter times 3.14. That is just short for a constant called pi. In our example, our tool starts out at a 1/2 inch diameter, which has a circumference of 1.57 inches. The 1.2 diameter has a circumference of 3.768 inches. It can then be said that the 1.2 diameter has an approximately 2.5 times greater surface than the 1/2 inch diameter. Therefore, if the RPM remained constant, the speed of the material going past the tool would be 2.5 times greater at the 1.2 diameter than it would be at the 1/2 inch diameter. In order to counteract this, what we need to do is alter the RPM depending on the diameter that we're cutting. Here is another very graphic example of how cutting at different diameters affects the cutting speed. In this example, we are showing a facing cut on a relatively large part, starting out at a 12-inch diameter and facing down to the center. Now let's assume that the RPM will remain at a constant 100 RPM during this facing cut. At the 12-inch diameter, the cutting speed relative to the tool would be 314 surface feet per minute. As the tool faces down towards the center line, it will eventually cross the 1-inch diameter. At the 1-inch diameter, the relative cutting speed would be 26 surface feet per minute. As you can see, the cutting speed, the surface feet per minute, is much lower the smaller in diameter that we get. To counter this, what we really need to do is increase the RPM as the diameter gets smaller. This will keep our relative cutting speed very constant. The feature, constant surface speed, does this automatically for us. With this feature, we would command G96 and tell the machine what surface feet per minute we want the machine to run at. Then the machine will go through and calculate an RPM for every diameter that the tool is cutting at. So under the effect of constant surface speed, the RPM of the machine is constantly changing whenever the x-axis changes diameter. Deciding on when to program the machine in either constant surface speed mode, G96, or in revolutions per minute mode, G97, is sometimes confusing for the beginning programmer. Generally speaking, you would use G96 whenever the tool will be cutting at different diameters, as in the case of facing operations, turning operations, boring, and grooving operations. You would select revolutions per minute mode with the G97 command when you are performing a single point threading operation, tapping, drilling, and reaming. Generally speaking, you would use direct RPM programming, G97, whenever you are cutting at a constant diameter. Selecting the proper speeds and feeds is always a challenge to any programmer. You have to refer to some form of documentation that outlines the specifications for cutting speeds and feeds relative to the workpiece material you are cutting and the tooling material. Oftentimes this documentation comes from the tooling manufacturers. We have a sample spreadsheet up on the screen right now that shows you some cutting speeds and feeds for turning, boring, and facing operations with coated carbide. Along the left side of the spreadsheet, you will see the workpiece materials. In this example, we are looking at 303 stainless steel. If we follow that to the right into the next column, that would be our machining operation, whether we're roughing or finishing. The next column to the right shows us our depth of cut. We'll get into that a little bit more later on. The next column, which is labeled SFM for surface feet per minute, is in the range of 300 to 650 SFM. As you can see, that is really a very large range. But keep in mind that 303 stainless steel can come in many different hardnesses, and that is why often you will see tooling manufacturers recommend a working range. You have to tune that to your specific workpiece material. In our case, what we will do is we will pick a number somewhere in the middle of that. By taking 300 plus 650 and dividing that by 2, we will get the exact middle of that at 475 SFM. To review again, for 303 stainless steel, the range the chart gave us. As mentioned earlier, to review again, for 303 stainless steel, the range the chart gave us was 300 to 650 surface feet per minute. We took 300 and added 650, which gave us 950. We divide that by 2, and that gives us 475 SFM. That's right in the middle of our working range. We'll use that as our starting value. Programming the machine to run in constant surface speed is very easy. We would command G96 S475 MO3. If you remember, G96 sets the machine into constant surface speed mode. The S475 was our SFM that we just got from that worksheet. The MO3 starts the spindle in forward rotation. It should be noted that we can only have one M code per line. This is a limitation that is built into most of the older equipment. Machines that are older than about 1995 could only have one M code per line. Some newer machines allow up to 5 M codes per line of program code. As far as the S word goes, it really doesn't make any logical sense to have 2 S codes on one line. It would be very contradictory to have an S475 and also, for example, an S300. The machine just could not figure out which speed to run at. However, with the M codes, it could seem logical to have more than one. For example, MO3 turns the spindle on, MO8 turns the coolant on, and that may be nice to have happen at the same time. However, on the older equipment, the first M code would be ignored, and only the second one would be executed. So if our command read G96 S475 MO3 MO8, our spindle would not start. A little bit later on, we will be showing you how to construct the entire program so that you get your coolant and your spindle running in the proper order and so forth. But for right now, just try to memorize that rule. Only one M code per line. As mentioned earlier, when we are drilling, tapping, reaming, and single point threading, we need to program the spindle in direct RPM as opposed to constant surface speed. For drilling, tapping, and reaming, this is especially important because if you notice, our tool will be moved to X0, meaning a 0 diameter. If we are under the effect of constant surface speed while we are drilling, the spindle would be rotating as fast as it can possibly go because it's cutting at a 0 diameter, or a very, very small diameter. That would cause constant surface speed to accelerate the spindle to maximum RPM. This is undesirable, as you can obviously tell. Just as we did for the turning example, we need to refer to a speed and feed chart to select a proper speed for drilling. In this example, let's look at 303 stainless steel. We follow along the left column where it's labeled work material, and we find 303 stainless steel. We move to the right to the next column, which is labeled SFM. In that column, it gives us a value of 100 for 100 SFM. We will use that in our calculation for calculating the correct RPM for this tool. In order to calculate the RPM for this tool, we need to know what diameter the drill is. For this example, we will use a 3/8 inch diameter drill. From the previous slide, we determined that when we are drilling in 303 stainless steel, we should be cutting at a speed of 100 surface feet per minute. Using the formula 3.82 times the SFM divided by the diameter would give us the RPM. The 3.82 in the formula is a constant. This is very similar to the numeric constant pi. However, 3.82 also takes into account the conversion from inch into feet. Our drill diameter is given in inches, 3/8 of an inch. Our surface feet per minute unit of measure is in feet. So the 3.82 takes into account this conversion. The SFM in our formula is our surface feet per minute, and that value we got from the chart on the previous slide. The diameter in our formula is the diameter of the tool. For drills, reamers, and taps, it would just simply be the diameter of the tool. But when we are single point threading, we would be taking into account the cutting diameter. For threading, it is almost always ideal to take into account the major diameter of the thread, the larger diameter. This way we know we won't be burning up the tool as the tool decreases in diameter during its successive cuts. Now we will move on to using the real numbers. 3.82 times 100, we take that value and divide it by 0.375, and that gives us 1018 RPM. Now you may come up with an unusual number. For example, 1018.667 or something like that. Don't worry about those extra numbers. RPM and SFM are always programmed using whole numbers. That means that anything after the decimal point we can just simply eliminate from our value. Turning the spindle on in direct RPM mode is very easy. We would command G97 S1018 M03. The G97 sets the machine into revolutions per minute mode. The S1018 tells the machine to run at our 1018 RPM that we calculated, and the M03 turns the spindle on in forward rotation. That's all there is to turning the spindle on under the effect of direct RPM programming. Let's do one more exercise. First, we will go through and calculate the RPM for a half-inch reamer. For this example, we'll say that this half-inch reamer needs to be cutting at 45 SFM. Using the formula, RPM equals 3.82 times the SFM divided by the diameter. We will then put our real numbers into that formula. 3.82 times 45. We'll take that amount, divide it by 0.5, and that gives us 343 RPM. Now that is what we would put in our program. Now there are times when you may be looking at a program, or you may be looking at an RPM in a program and a specific tool diameter, and you may want to know what SFM it's cutting at. To do this, let's just reverse the process. We'll take the half-inch reamer running at 343 RPM, and we will run that through the formula SFM equals diameter divided by 3.82 times the RPM. So we take 0.5, the diameter of our reamer, divided by 3.82, our numeric constant. Take that amount and multiply it times 343, the RPM, and that gives us 44.89 SFM. If we round that number up properly, it comes out at 45 SFM, exactly where we started at with this example. These are two very handy formulas, and I highly recommend that you take notes carefully on them. You will be using these formulas time and time again when you are programming. These formulas also come in very handy when you are troubleshooting cutting conditions out at the machine tool. Let's take a look at how we can call up the tools and work with those offsets. Most CNC turning centers utilize a turret for mounting the tools. A turret is a large disc with a means of fastening the tools to this disc. The turret rotates clockwise and counterclockwise. The machine itself will decide which is the fastest way to get the tool into the cutting position. So the machine will automatically determine whether it should rotate clockwise or counterclockwise to get your tool into position. On some machines, they allow you to program which rotation you would like to use. Oftentimes this is done using a special M code. Care must be taken when mounting the tools onto the turret. You need to provide adequate clearance between each of the tools. This is especially important when we have OD tools next to ID tools. As a programmer, you need to be aware of the limitations of each machine that you'll write a program for. With these limitations in mind, you will select the proper station to place the tool. It should also be noted that a typical mistake most beginning programmers make is to select tool numbers based on their order of usage. For example, if their first tool is a turning tool, they would call that tool 1. The second tool perhaps is a drill, and they would call that tool 2. And then the third tool might be a boring bar, and they would call that tool 3. This is not the correct way to do it. You should try to pick dedicated stations on your turret for OD tools and ID tools. This allows you to decrease the amount of setup time by dedicating certain stations on your turret for very common tools. This oftentimes is developed over a period of months or years when working with a CNC machine. You will find that you will always use certain tools on almost every job. Those are the tools that you will focus on when selecting dedicated stations on your machine. Programming the machine to call up a tool is really quite simple. We are going to use the T code to call up a tool. However, the T code calls up two things. In this example, we have T0101. The first two digits, 01, call up the tool. The second two digits, 01, call up an offset. We'll discuss offsets in a few minutes. It is important to understand that we can call up tool 1 with a different offset. For example, T0131. That calls up tool 1, offset 31. At first glance, this may seem a little bit odd or unusual. However, calling up a tool with a different offset number is quite frequent. We really should take a look at formatting of the word. The T code must use 4 digits. This is why we would program T0101 instead of T11. This is required because of the double purpose of the T code and how the machine would read that command. The machine is expecting to see a T word followed by a 4-digit number. The machine knows that the first 2 digits will be the tool number and that the second 2 digits will be the offset number. You will find that there are many codes that require a specific number of digits. Oftentimes you will only need to add a leading 0 to the numeric value. If you remember back, for coolant, the command was M08. Well, the actual value is only 8, but on older machines we needed to have those 2-digit numbers. So that forced us to have M08. It is very important to know that when you have to format a number to a specific number of digits, that we have to add the 0 at the beginning of the number. Otherwise, if you add the 0 at the end of the number, it's like adding 10 to it. For example, to get from T1 to a T01, if we screw up and put the 0 at the end of the number, we would have T10. That would mean T10, a whole different ballgame. So watch out for certain words that require an exact number of digits. The T code is the most critical. Here we can get a good look at a program. Granted, this is not a complete program. However, it does give you an idea of the logical flow of a program and the order in which we must program things. Program execution always begins at the top and works towards the bottom, just as how you would read a book, from left to right, top to bottom. The first thing we would probably need to do is call up our tool, then get our spindle running, and then go through our series of cutting motions. What is important to note here is that the T0101 command remains active during the entire cutting operation. So offset number 1 is active during this entire part of the program. There are several different types of offsets on the machine tool. For now, we will focus on wear offsets. If you can imagine, as the tool is cutting a series of workpieces, the tool would begin to wear. As the tool wears, it is cutting less material. And with each successive part, the tool will wear a little bit more. Now, the setup person or the operator needs to be able to adjust the machine to take into account this tool wear. This is needed so that we can maintain accurate size of the workpiece. If we did not have offsets, we would literally have to either adjust the tool the way we did on older automatic mechanical equipment, or we would have to reprogram the entire job taking into account this tool wear. Either way, it's a very time-consuming process. The wear offset allows us to input a value shifting the tool by a certain amount. For example, if our tool had worn 1/10 of a thousandths, our workpiece would become 2/10 of a thousandths larger in diameter. When we go to offset this tool, we simply need to tell the machine how much smaller in diameter we would want to make the part. In this example, we would want to make the part 2/10 smaller. So we would put in an incremental offset of 2/10 of a thousandths. Let's take a look at how all of this fits together from a programmer's point of view and from an operator's point of view. On the machine tool, there is a special place where an operator would put offsets. Now, these offset values shift the position of the tool all the while the tool offset is active. In our little program at the left of the screen, that offset number 1, called up by the T0101 command, remains active during the entire cutting operation. Now, if we look at the T0101 command, we see that we're using offset 1. If we look over at the screen from the machine tool showing the offset wear page, we see that offset number 1 has an X value of 10 thousandths and a Z value of 2 thousandths. That means that every X position within the program will be shifted 10 thousandths in the plus direction on X-axis, and every Z movement will be shifted 2 thousandths in the Z plus direction. Now again, tool 1, offset 1, remains active during the entire cutting operation. At the next tool, if we were calling up tool 2 using the command TO202, we would activate offset number 2, which would then shift all of the coordinates for that tool minus 2 thousandths on the x-axis, with no shift at all on the z-axis. This gives the operator tremendous control in maintaining the size of the workpiece. Again, an offset value could literally be as small as 1/10 of a thousandths. That gives you great control over the precision of a workpiece. It is also important to understand that in the command T0101, we are specifying offset number 1. We are not specifying an amount of shift. The amount of shift is stored on the offset page of the control. It's a separate area within the control that allows setup people and operators to input these values. They do not directly alter the actual x and z coordinates within your program. Depending on the machine type and how it is set up from the factory, your control may automatically cancel tool offsets. You have to determine first if the machine automatically cancels the tool offsets. If it doesn't, you will have to do this through your program. And that is accomplished quite simply by just programming TO100, as in this example. TO1 calling up tool 1 again, and 00 at the end of it calling up offset 0, which basically cancels any offset. So again, to cancel an offset, you would call up the same tool, but specifying offset number 00. So far we have only looked at the wear offsets. There are basically 3 types of offsets: wear offsets, geometry offsets, and work shift offsets. Both geometry offsets and work shift offsets really relate to the setup person. Those offsets will be covered in the setup lessons. Let's take a moment and review what we've covered in this entire lesson. M08 turns the coolant on. M09, coolant off. M03 turns the spindle on in forward rotation. M04 turns the spindle on in reverse rotation. M05 turns the spindle off. G96 and G97 both select a mode for the spindle speed. G96 selects constant surface speed mode. And if you remember, we use that type of spindle control when we are turning, boring, facing, and grooving. G97 selects revolutions per minute mode, and we use that mostly for drilling, tapping, reaming, and single point threading. The S word specifies the spindle speed. If we are in G97 mode, revolutions per minute mode, the S word would specify the RPM. If we are in the G96 mode, constant surface speed mode, the S word would specify the surface feet per minute that we want the spindle to run at. The T code calls up a tool and an offset. The first 2 digits of the tool number specify the tool number. The second 2 digits specify the offset number. You should remember we can have a different offset number for the tool. For example, T1213, meaning that we would have tool 12 offset 13. But in most cases you will find that the tool number and the offset number match. Well, that about wraps up this lesson. That means the quiz is next. It's quiz time! You will have to answer 10 questions during this quiz. Each of the questions within this quiz are a multiple choice question. Read all of the answers and click on the button that you think is the correct answer. Your score will be presented at the end of the test. Which of the following statements would be true? The command G96 S600 M04 does what? The command T1021 does what? The formula 3.82 times the SFM divided by the diameter is used to when selecting a cutting speed, you will under the effect of G97, which of the following statements would be true? When the program is run, it is executed in which order? Under the effect of G96, which of the following statements would be true? Wear offsets are used to the command T0314 tells the machine to You made it. Now take a moment to go through an evaluation to see what your next course of action should be. If you scored 0 to 50%, you should review the entire lesson. If you scored 60 to 80%, review the trouble areas where you had the most difficulty understanding. If you scored 90 to 100%, great job. Continue on to the next lesson. But before you do anything, what we need you to do is to enter your name. Take the mouse pointer and move it into the box next to student name. Click the left mouse button once, then type your name. After you have your name entered, a button will pop up at the bottom of the screen that says Print Quiz Score. Make sure your printer is ready. When you are absolutely sure that the printer is ready to print, click on that button. Good luck, and we'll see you in the next lesson.